better or lack is better. I don't know why. Um, play computer inner product space, etc., etc. And last week we talked about orthogonality, and we finished with מרחב הניצב, whatever we call it in Hebrew, I don't remember. How did they call it in English? Maybe I should consulate with the lad from last week. We called it the orthogonal space. Okay, which is logical. How? We defined the orthogonal space which is the product over some field F, and let be, I know, S subset of V. The or so, oh, yeah, no, space of S is within a set of all vectors in V that are orthogonal to every vector in S. For every U S, the product of V and U is 0. And we wrote down examples. Last week, let's write down another example so we don't be over that. For example, let's say R2 with a standard inner product, the example of something similar we did last week was S, I don't know, let it be the vector 0, 1. We have the orthogonal space is all the vectors in V such that the multiplication is 0. Now we only have one vector. In S, it's only 0 to 1, so it's all the vectors A, B in V such that the multiplication or product of 0, 1, and AB is 0. Now we know how to calculate the standard product in R2, generally speaking, in Rn. It is 0 multiplied by A plus 1 multiplied by B, which means that B must be 0, and we get the following subspace. The S nitzav here, the S orthogonal, is all the vectors of the form 0, something 0, which is the span of 1, 0. We defined
Is
this.
S the span? Like the set S should
What?
be the span of 0, 1?
No. S can be any subset. Now, my first written in the name, as we mentioned last week, uh, right in front of me with my bare eyes. Well, I decided to say that, yeah, S is a subset, nothing more, but the orthogonal space just as S, the orthogonal space is actually a subspace. Is a sub space of doesn't matter with what S is. Probably if one wants to be extremely formal, you can state that S is not an empty subset. But more than that, we can always talk about any set and calculate its subspace. Now let's add it. If I've already mentioned it, S is not empty set. That's gonna be weird if it is. Okay, let's prove it. We use don't know how exactly errors called it last semester. I called it in Hebrew the criterion המקוצר, the short criterion. If we want to prove that a subset is actually a subspace, we have to prove only two things: that zero is in this subspace, and it is closed under the operations of summation and multiplication by a scalar. So we need to show two things. One, that zero is in S perp, or every whatever S is, again. And secondly, let some U and V be an S perp, and let A in F, then the linear combination AU plus V is in S perp as well. You can try. The problem is that the lights are vertical, and the board is horizontal. Open the windows a bit. Now, by the definition of S-perp, it's not going to be, shouldn't be very tough. So, one, zero is it? Efestasha. Where's the Efestasha in Israel? Efes it's here, the Gushdan. Efes2 is, I don't know what it is. Phone number starts with Efestasha. Which region is it? Hamas. Now we know that we proved it last week. Zero is orthogonal to every vector. We know that the multiplication of zero and some vector is always zero. Sharon. Okay. Someone from Netanya, I don't know what. For every U in the space, in all the space, and specifically that's you write it? Yeah. Okay. And specifically, it is so for every U in S. So by definition, magic words, we do have that 0 is in the orthogonal space, whatever the set S is. I don't know if you can read it in Hebrew, it's small, but whenever I push too much space, it's like, you cannot type two consecutive spaces. Yes, you cannot. Please, what is it? Please read the the lecture about yeah. Be ashamed, you literate fuck. Okay. Yes. Two. We have U and V and UV here, whatever. So we know that the multiplication, I already used U. So let's use W or something. No, let's change W here. I want you to delete whatever you've already written to erase. We know that the multiplication of U and W and the multiplication of U and of V and W is 0 for every W in S, because we know that they are in S perp by definition, and we need to show, semicolon, we need to show that the multiplication of W with AU plus V is 0 as well. And again, for every W in S. Indeed, by the basic properties of inner product, it shouldn't be hard. Linearity in the first coordinate gives us a UW plus VW, and we know that both are 0, so it is 0 all the way. So by the short criterion, we know that the orthogonal space is always actually a space, just as in its name. And I want to continue with these kind of propositions. Each one is not very difficult to understand or to prove. And when we finish what I want to say about Esper, about the orthogonal space, we can move on to the next subject of projections, which is more I don't know, interesting, complicated, whatever. Of course, we'll continue with this next lecture. And next week, Bezrat Hashem, we're not going to have a lecture, right? We already talked about it. So don't peer, don't come here inside. 10 בטבת. It's day of fasting. We do not eat, so apparently Baran you cannot teach as well. Other institutions you don't have this holiday. Yeah. Yes, but they do like to, in Hebrew, say, למשוך את החבל, to pull the rope a bit more than needed. Yeah, we're gonna have, you saw it last year, in Jerusalem Day, it's a holiday. I don't know any other institution that celebrates Jerusalem Day. They would, yes, it's not in Jerusalem here. Okay, let's move on with another propositions. What about, it's a nice question. What happened when we look at the orthogonal space of the orthogonal space? Meaning, what is the perp when the computer wakes up or the internet wakes up or whatever is, yeah, you can see the parenthesis. Your internet connection is not stable. Yeah, I already understood it. It's not my fault. So, no, I have to write it down here. Yes. The orthogonal space of the orthogonal space. What should it be? Yeah, seems intuitively true, but not every S does it. If S is a subspace, then the orthogonal space of the orthogonal space is equals S itself. If yes, this is what I want to say. Generally speaking, generally the S is contained in the orthogonal space of the orthogonal space for every subset S, not just for subspaces. Let's prove it. I think I want to prove the second part of the proposition. Let be some V vector in S, and we should prove that which is contained in that. It is true as well, but I think we'll leave it for later, maybe. Now, let be some V in S. We need to show that V is in the orthogonal space of S. By definition of the orthogonal space, let, I don't know, U be some vector in S first, and we need to show that the product multiplication of U and V is 0. Want to be in the orthogonal space, you should be orthogonal to every vector in the set. Now, the set here is S perp itself. Indeed, U is in S, then copy it. U is in S orthogonal, and V is in S. So, just by definition, we do have multiplication 0. Now, it doesn't work the other way around because we can take a set of 1 or 2 vectors, just in a basic example. And when we look at the orthogonal space of S, we get, as we already proved, a subspace. Specifically here, it's the span of 1, 0. When we look at the orthogonal space of this space, we do not get only the vector 0, 1 itself. We get the span of 0, 1, which is, of course, greater and contains the vector 0, 1, but not vice versa. When you start with not just a subset, but with a subspace that is close to multiplication by scalar and summation, etc., then doing the
because for every a, S orthogonal has 0, so every other vector is in S orthogonal, right?
No, but in orthogonal, you have to be orthogonal to every vector in S, not just to one of them. So being orthogonal to 0 is not enough. Okay, this is the first, this is the proof of the second part of the proposition. You know what? Let's continue. Let's explain why the other direction is true. I mean, we've already proved one direction of the equality. Now we need to prove the other one. For the other one, it doesn't work all the time, just for subspaces, as we already mentioned. For the opposite direction, we assume that S is a subspace and not just subset. Um, Sammy, you hear me?
Yeah.
Yeah, it's a problem with my own computer. I tried to fix it.
Try to move the
Yeah.
mouse 1 second from the computer.
What?
Try to move the mouse from the computer 1 second to see if it's still working on the screen. No, from your own.
Yes, I understand. It doesn't. It went to sleep. We're good. Okay. Okay. Let's try to figure out what the problem is. This looks might have policy. Why did you go to sleep? What is wrong with you?
Me? I didn't fall asleep yet.
No, you're totally fine. I mean, you can go to sleep, but you're not going to see it because you are I'm sharing my screen. I
Yes.
don't know. What is No, it is it's fine. It just I don't know what's wrong with it. Thank you.
Do you check if it's working?
I don't know what is it. It is resurrect what?
Do you check if the charging is working?
Yes, the battery is full. 3 minutes to full recharge. Okay. Well, I don't know. That was extremely weird. Now, my computer is not young. It's more than 5 years old, and I don't really take care of it. And maintenance, talking about. But I shouldn't just, turn off for some reason. Okay, but it's a miracle. Resurrected. It's alive again. I mean, it's Christmas soon, right? Yes. In the spirit of most beautiful time in the year. How does the song goes? Something like that. Yeah. Jolly. Yeah. We assume that S is a subspace. Now it is recording. We share screen. Yeah, everything is good. What's wrong? Oh, that's not good. Control S. Let some vector V in S orthogonal, and we need to show that V is in S as well. Okay. By definition, we know that V and U is 0 for every U in S perp. I'm afraid that we need to work with basis and basis, orthogonal basis for S and S perp, etc. It is true, but I don't think I want to elaborate about it right now. It is in my plan for the next lecture, probably. So, I don't know if it's the right spot to prove it, actually. Okay, let's prove it. Okay. Um, let let's call it V1 to VK, be an orthogonal, and one can use orthonormal, which is fine. Orthonormal, ortho with the R. Normal, basis of S. We know it is subspace, it has a base. We can complete it to an orthonormal basis of all V and some vectors V1 to VK and then VK plus 1 to some Vn. Now, I claim that the additional vectors from k plus 1 to n are an orthonormal basis of S perp. Because these, by definition, the vectors that are orthonormal to the vectors v1 to vk that span S. And then if we know that a vector, that is good, yeah. If a vector in V is in S is a linear combination of V1 to Vk, and it is perpendicular to some vector u in S perp, then it must be u some linear combination of the additional vectors Vk plus 1 to Vn. Let's write it down that way. The set of the additional vectors is basis an orthonormal basis for S perp. Now I think I'm getting too deep into the rabbit hole for the specific claim I want to claim here. So as I mentioned, one direction is easy, the other one is true, but in order to prove it, I think we should right now move on and define some new definitions, not right now, but short time. And then by that we can prove our claim. Considering it myself, maybe I should do it right now, and that's it. So you know what? Hmm, Intuitively, it is true. Okay, the rest are of S. It's orthonormal. The multiplications, the products are zero. So whatever you take from here, E belongs to S perp, and moreover, it is spanned by this set of vectors. So it is a basis, not just subset of S perp. No, I came to a conclusion. I want to delay it, linger. Talk about it later. So how will we about it? Let's convert it written and either D. So preferred color, purple. We will continue. Let's continue later. Bezrat Hashem. I don't want to get too messy right now. Yeah. Okay, what else do I want to say about the orthogonal space? Another two more proposition, and I think that's enough. And then we can move on to the subject of projections. Okay, proposition. Let V blah 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 A, B subsets of V if A is contained in B, then when we look at the orthogonal spaces, the orthogonal space of A actually, no, subset F, right? Subset wants to the other way around. How do you do it? I just turn around here. No, no, no. I know how to do it. It's subset. Okay. You see. Subset X contains B. Intuitively, it is correct. In order to be in A in B perp, you need to satisfy more conditions because there are more vectors in B that you need to be orthogonal to. But let's write it down explicitly. Let be, I don't know, some U in B perp, semicolon. We need to show that U is in A perp as well. By definition, it is pretty easy. The product, the multiplication of U and V is 0 for every V in B. Know that A is contained in B. So if this equation holds for every vector in B, it is specifically holds for every vector in A. And so if it is orthogonal to every vector in A, it is indeed in A perp. This is my proposition and proof, and another one last proposition I want to prove. Then we can move on. Any questions about that proof? The proof in purple. We'll continue later but from different approach probably. Okay, so for my last proposition in this session of propositions, if we look at some subset A, let S be a subset of V, then the orthogonal space of S and the orthogonal space of the space spanned by S are the same. We've already talked about it when we looked back in our example from the beginning. You know, if it's 1, 0 or the span of 1, 0, it's practically the same. Answering the question, okay, which vectors are orthogonal? But let's prove it once and for all. On one hand, we know that S is contained in the space it is spanning. True for every step, every time, every space, every whatever. So by our last proposition, we have that the span of the orthogonal space of S contains the orthogonal space of the span of S. It's A and B by our last proposition. And we need to show the other direction, which is on the other hand, let's write it down. On the other hand, we need to prove the other direction. So let some V in S perp. Show that V is in the perp of span S. What V, U, whatever letter it is. For that, by definition, let be, I don't know, some V in the penis. Without the perp, it's penis itself. And we need to show that V and U are orthogonal. The multiplication of V and U is 0. That's what I want to show. If it's in S perp, it's in span S perp, meaning that it's orthogonal to every vector in span S. Now, by definition of span, yeah, by the definition of ST, there are some vectors, I don't know, V1 to Vk in S and some A1 to AK in F, such that the vector V is the linear combination A1, V1, etc., etc. And K, whatever the index is. We know that U is in S perp. And all the vectors VI are in S. So U and VI are orthogonal for every I. Right now, if we write U and V, and it will be more convenient to write V and U to put V in the first coordinate, we can write down V as the multiplication, the linear combination of A1, Vy, etc., etc. And using the linearity of the first coordinate, if we started with V in the second coordinate, it wasn't very different. Wouldn't have been very different, just putting the conjugate, the complex conjugate over the heads of the scalars. But right here we can plug it out, A1, V1 and U plus blah, 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 AK, VK and U. Because of the linearity of the first coordinate yet again, and each and every one of these multiplications, these products, is 0. A1 multiplied by 0, blah, blah, blah. AK multiplied by 0, which is 0. As required, we need to show that U and V is 0. That's what we get. Okay. Any questions about our proposition? Okay. So we move on to our next subject, yet again, as I stated 2 weeks ago, inner product spaces is the big title all over what's left of our course, but move from small subject to another, and this next small subject is projections. From the linear algebra point of view, of course. What is a projection? Let's write something down. Let V be an inner product space. I remind you that we talk about finitely generated spaces, meaning that they have a finite basis, not an infinite one. And let U under V be a subspace. Let U1, U2, till UK be an orthogonal basis of U. The projection of let another lesson. Let V be in V. The projection of V on U is denoted with the letter pi. We can use P, proj, whatever you like. Pi U of V, and is defined by what is the definition of the projection? We have the product of U1 with V divided by the product of U1 by itself multiplied by U1. And the same thing for U2. So on and so on when you get to UK. Looks weird. Example right away. When, and that's what I recommend to do when you have a specific question with specific subspaces, etc., etc. Use an orthonormal basis, not just orthogonal, when the basis is orthonormal, so the multiplication of the vectors with themselves is just 1, we get that the projection of V on U is the multiplication of U1V multiplied by U1 plus blah, blah, blah. UK and V multiplied by UK. Want you to note something, then we'll have an example, then we'll talk about the properties of this weird looking guy. Note in lecture number 8, it was fun. We say that for every U1 to UK, but it continuing with UK plus 1, blah, 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 till UN basis of orthogonal basis of V, and for every V and V, we have a way to write V down as a linear combination of the vector of the orthogonal bases. We know what the scalars in the linear combination are, and these are the scalars. I mean, generally speaking, you move forward, march forward, we carry on. So how we said before to UK plus 1, and we finish with UN. But in some way, that's what I want you to note. Notice the projection is just the part of U from the linear combination. And so the projection on U is the part without just the part of the linear combination that belongs to U. Let's write down a simple example. Then we can ask some questions. For example, let's look at V, which is, I don't know, 3, and U that is the span of 1, 0, 1 and minus 2, 0, 2 with the standard inner product. Now, we already have an orthogonal basis, and one can easily normalize the vector in order to achieve an orthonormal basis. A good question, we'll ask it later, not of today, maybe later on. When we get a subspace spanned by some basis that is not orthogonal, how can we find an orthogonal basis to the same subspace? Now, to find an orthogonal basis to all the space, the whole space, is probably pretty easy. We actually can. No, that's not my problem. What is it now? Huh?
Yeah.
The electricity in, but as far as I can see here, oh. Electricity here is working fine, and the computer in class working fine as well. Yeah, the projector is. Do you mind
I think it might be a brown.
getting on the table?
What happened?
What now? Yeah. Sammy, that's a great question. What now? Right now, the projector in the class decided to go on a break. Um, okay. Wakey, wakey. Okay, I pause. So, as I started to say, one can ask himself, okay, when I get a subspace with a basis, but the basis is not orthogonal, how do I find an orthogonal basis to the subspace? We'll deal with that question later. Now we've already started with something that is orthogonal. The multiplication, the product of 101 and minus 202 is actually 0. Note that this set is orthogonal, the standard product. For you will spend by this set of two vectors. It is a linearly independent set, so it is a basis. It's not basis for R3. No, but it's a basis for you. Yeah. Is orthogonal. So I don't know, some vector in V, 1, 2, 3, for example, by definition, the product projection of V on U is this nice, magnificent multiplication. It's 1, 0, 1 with our vector V. And this specific example is 1, 2, 3 multiplied by 1, 0, 1, and it's all over again, but for minus 2, 0, 2. Okay, we know how to calculate this. What? No, you're absolutely correct. My mistake. We multiplied the vector. Huh? No, but I already told you that in the last month, whenever I start a conversation with GPT, with Gepet, I always told him, first of all, Gepet, how are you? Please turn on absolute mode. Yeah, I told you about it, right? All the bullshit of, oh, it's a great question, and the smileys, etc. Fuck off. So, answer me. Thank you. Okay, but as I mentioned, whenever the inner product isn't specifically mentioned, it is the standard one. So we know how to calculate these multiplications. 1 multiplied by 1 plus 0 multiplied by 2 plus 1 multiplied by 3. And 1 multiplied by 1 plus 0 multiplied by 0 plus 1. If I'm wrong, is your duty. Correct me? And something similar. 2 multiplied by 1, 0 multiplied by 2, and 2 multiplied by 3. And minus 2 multiplied by minus 2, 0 multiplied by 0, and 2 multiplied by 2. Minus 2, 0, 2. What do we have here? It is 4 above 2, which is 2, as far as I can see. And here it is minus 2 plus 6 is 4 above 8, which is. And our final answer is 1 0 and 3, as far as I can see.
Can we see what this means geographically?
What?
Can we see what this means geographically?
When it comes to R2 or R3, one can explain it geometrically what is going on, talking about the standard products. But I want to write down a theorem, and one of the parts of the theorem talks about what the projection of V on U actually is. What is so special about this vector? Any other questions? So let's write down the theorem, and then we can move on to our break. When we return, I shall decide what are we going to prove this theorem, what we are going to use as something known. We already proved some propositions. Theorem, so let's start it nicely. Let's copy it from here. Be a subspace, blah, blah, blah. Let's vector V in V. So first of all, one can see pretty easy that the projection of V, whatever V is always in U. Basically, by definition, U is spanned by U1 to UK, and the projection is a linear combination with pretty ugly scalars, but still linear combination of U1 to UK. Secondly, if we take a vector from U and we try and calculate the projection of V on U itself, then we get V, and vice versa. The projection of vector is the vector itself, means that the vector is in the subspace. Moreover, if the projection is 0, some vector V, it means that V is a linear combination of all the other vectors, U, K plus 1 to UN, that are not in U, which means, that's what we've already started to mention in our purple text, it means that V is in the orthogonal space of U. Another another thing I can claim about the projection, for every vector V, you take V and you subtract its projection on U from itself, it is always in the orthogonal space of V. And least but not last, whenever we do, I don't think we're going to prove it, at least not today. Some of the other properties maybe we'll try to prove when we get back from break. What is actually the projection of V on U? The projection of V on U is the closest, the most close vector, the closest vector to V in U. Formally, for every u in u, we have the distance, which is the norm of the difference between v and the projection of v on u is less or equal the difference, the norm of the difference between v and u. Whatever vector in u you take, the difference between v and u is greater or equals the difference between v and the projection. As well as we mentioned, the projection is vector in u. So by these terms, the projection is the closest vector to v in the subspace u. Okay. Any questions about the way we stated our theorem? Well, it's 1, 2, 3, 4, 5 sections. Okay, so it's a good time to go on our 15 minutes break. Of course, netto, so 1 and 31 minutes we shall continue. I stopped the recording. Please remind me to record again. Okay, so back online. Let's prove this theorem. Move one by one and see what is easier or less easier. Proof. So let U1 to UK be an orthogonal, doesn't matter, basis of U. There is a hidden assumption here that it doesn't matter which orthogonal basis we take, we get the same result. It's not so obvious, and we'll discuss it, but probably in the next lecture. Let U1 to UK, we want to talk basis of U. So first of all, by definition, the projection is a linear combination of U. The projection is a linear combination of the elements of the basis, and so it is indeed in U. That's an easy part. For number 2, we want to show that the vector is in U if and only if the projection of itself is the vector itself. That's what we want to show. So on one hand, if we already know that the projection of V is just V by what we already proved in number 1, by 1, we know that this is a vector in U for every vector V. And so V is in U. So the projection equals the vector itself. The vector must be in U, the subset we project on. On the other hand, let V be in U for the opposite direction, and we need to show that V is, or the projection of V is just V itself. Okay. Um, but something we already talked about last lecture number 8. Indeed, V is in U and U1 to UK is an orthogonal basis. Lecture number 8, that was great, but we know it was fun. We proved that in this case, we know how to write V as a linear combination of U1 to UK. We know what the scalars are. And what we stated in lecture number 8 was actually this one. We know that the scalars in the linear combination are these weird multiplication. We proved it in lecture number 8. And on the other hand, by definition, this is the projection of V on U. On the other hand, it is the projection of V on U, so we have indeed V and the projection of V are the same. Now I used this something from last week that one can write down any vector V as a linear combination of the elements of the orthogonal space when the scalars are this weird multiplication. So this gives us 2. This 2. Let's write down what do we want to prove in every. How do you say safe in English? Paragraph is a pska. Okay. Good question, but not our main question. For the third part of the theorem, we want to show that the vector is in the orthogonal space of U if and only if its projection is on U is 0. Okay, so on one hand, if we know that the vector is in the orthogonal space, then section, it's okay. Section, then the multiplication, the product of V and UI is 0 for every UI in the basis of U. It is true for every vector in U. Specifically, it's true for the vectors in the basis. So we have the linear projection defined as the linear combination in which every scalar, every coefficient is just 0. It's UK, UI, U1, U2, U3, blah, 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 are orthogonal to V. So indeed, if we take a vector from the orthogonal space, its projection on the space itself is 0, but we should write it down for the opposite direction as well. if we know that the projection is 0, why does it mean that the vector itself belongs to the orthogonal space? Ah, I almost forgot. Brought you some confectionery. That's the right word. Yes, you're a small group. Sammy, you come on Sunday, mashallah, and I'll bring you as well. So you can take. I mean, it's let's say you're a small group, you can take whatever you want. And just there are other groups that didn't received yet. Okay, haven't received yet the you bon appetit. They're all this practically the same taste, I think.
Yeah, ours.
Yeah. I told myself class of 8 a.m. after I don't know the exact English word for about some dozens of snakes. I love the snakes. Should stop yourself from eating more. But so many classes, so many temptations. On the other hand, if we know that the projection is 0, we have that the projection is 0. Okay. And what do we have here? This is a linear combination of the elements of a basis of U. U1 to UK is a basis of U. Therefore, it is a linearly independent set. So when the linear combination of linearly independent vectors is 0, only one way out. Every coefficient, every scalar is 0. So every scalar is 0. Ui multiplied by v above ui is 0, which means that the multiplication of v and ui is 0 for every I. Write down that way. This one line is just, to space things. Here the leaks, nothing mathematical. And yet again, U1 to UK is a spanning set for U. No, first of all, by definition, every UI is in the orthogonal space of U, because it is. No. No, sorry. By definition, we know that V is orthogonal to every U in every UI in the subspace. So V is in the orthogonal subspace of U1 to UK because it is orthogonal to each one of them. By one of our previous propositions, we know that if a vector is in the orthogonal space of some set, it is in the orthogonal space of the span of this set as well. And from one of our previous propositions, we get that V is in the orthogonal space of the span of this set, which is U, because U1 to UK is a basis for U, for me and U. This is the opposite direction in section 3 of our theorem. If we do know that the projection is 0, then vector V must be orthogonal to every UI. So orthogonal to every vector in the basis, you are orthogonal to every vector in the space. Any questions about number 3, 2, or 1? B. We're simple creatures. You hide temptation. It is less tempting.
Oh,
Yeah.
Orthogonal to you. It will make sense.
Yeah. And you know, that's how I feel. In linear algebra, most of the theorems are intuitively true, make sense, are kind of, I mean, you can do it as an exercise in the practice, right? Or in the homework, it will be totally acceptable. It's not proving some exhausting theorem in V1 or 2. It's different kind of theorems. Okay, what about number 4? It's not an if and only if statement, which is already better. And right here, we want to show that the difference between a vector and its projection is always in the orthogonal space of U. So in order to do that, we shall take some vector in U and prove that the projection is 0. Let be, some U and U, semicolon. We need to show that the multiplication of V minus pi UV and U is 0. And then by definition, the vector V minus pi UV is going to be in the orthogonal space of U. By linearity, it is equivalent to V and U minus pi U V and U equals 0. And this is true if and only if the multiplication of V and U, the multiplication of pi U V and U are the same. Multiplication, the product, whatever. How can we show that these multiplications are the same? I think that we should get our hands very dirty. Write it down explicitly with as an linear combination of the vectors of u. Okay, so on one hand, we know that by definition, the projection is this ugly thing. It's weird. Okay. Hopefully change anything. Nothing is only visible when you move to the PDF. One should try to catch them in the leaks. This is the orthogonal projection, and that there are some scalars a1 to ak such that the vector u is a1 u1 blah 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 ak uk. Yet again, u1 to uk is a basis for u. So specifically, every vector u in u is a linear combination of u1 to uk. This is a1 u1 blah 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 blah. Right now, let's write down these multiplications explicitly, and hopefully we will get the same thing eventually. Space here, better. Yeah, any questions, Sammy?
No, good.
You good? Okay. On one hand, the multiplication of v and u is the multiplication of v and this lovely linear combination. Now, I wrote down u in the second coordinates, which maybe should be written in the first coordinate in the first place, but doesn't really matter. We know that when we have a linear combination in the second coordinate, the scalars get out, but with the conjugate. It's in the second coordinate, so it is the conjugate of a1 multiplied by the product of v and u1. This little hat, the conjugate, coupled conjugate over a1, surprisingly visible. In the projection here in both of the 604 classes we study, the projections are good. There are projectors, turbo projectors, the lines always missing and that stuff. Now, the conjugate of AK and the product of V and UK. On the other hand, if we write down the multiplication of and the projection and you get something ugly in the first place, but we've already done uglier things last week. We know that this nice multiplication contains sums of orthogonal vectors. So multiplication of u1 with u2, u1 with u3, u3 with u5, etc., are all 0. What is left? What is left for us? Only the multiplications of the vector with itself. I mean, u1 with u1, u2 with u2, etc., etc. One can write down, first of all, okay, it's the sum of all multiplications. No, let's write down specifically. Now the set U1 to UK is orthogonal. So the multiplication, the product of UI and UJ is 0 when J and I are not the same index. We are left with the multiplication of U1 and U1 and the multiplication of U2 and U2, blah, blah, blah. Multiplication of UK and UK. Yeah, Sammy, you are from the UK, aren't you?
Yes, indeed I am.
Mm-hmm. Now, the scalars from the first coordinate get out without any problems. The scalars from the second coordinate, they receive a nice little conjugate hit. So it's A1 multiplied by U1, U1. Blah, blah, blah. It is UK multiplied by, divided by UK, 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 UK. And how surprisingly nice, the denominators canceled with the multiplication of the product themselves. So we are left with this kind of linear combination, but right now something about the placing the places of the vectors in the inner product is off. I mean, on one hand, you multiply the v by u, so v is in the left hand of the coordinate. On the other hand, by our definition of the projection, we put v in the second coordinate. And this is my mistake. Did I write it down from the beginning? Yeah. I'm mistaken here. I'm thinking real numbers, so it doesn't matter. But generally speaking, yet again, it's probably some kever rachel or something, right? My bad. The exact definition of orthogonal projection is with the vector in the first coordinate, not in the second. Just as we talked about the scalars in the linear combination last week. I talked about real numbers. The example talked about real numbers, so it doesn't matter. But mathematically, technically speaking, it should be the other way around. It should be v on the left coordinate and ui in the right coordinate. So let's good with it. I wanted to prove every part of the theorem, unusual, but we do have time. I think these proofs are more proofy to do. Some ugly calculations of matrices. Yeah, that's what I want to say. What did I write down explicitly? No, it's in lecture number 8 we did, that was my bad. We already told it. Yeah, it's V on the left coordinate, not on the right one. Thinking about real numbers, you end with real numbers. So my bad. Let's change it wherever needs be. First of all, here it's with V on the left hand of the product. Secondly, here. Thirdly, here. You say fourthly? How do you say it in English stuff? Then and for moreover, furthermore, yes, nevertheless, okay. Blessed be the control C, blessed be the control V. How great I am. Okay, one tiny typo, but an important one. Okay, so right now, yeah, we do have the same multiplications. V with U gives us this linear combination, and pi U V with U gives us the same linear combination. Indeed, we get the same multiplication as all we already mentioned. When we started this proof, it is enough to show that the difference between V and its orthogonal and its projection is in the orthogonal space U. Okay, so one little fixing, razzle dazzle, we get what we need.
But why does it matter that it was in the wrong order? I thought it's fine.
Because
Like the
generally speaking, we can talk about and we need to talk about, we need to refer to inner products when the field is C, is the complex numbers.
oh
And
right.
of the complex numbers, changing the order of the vectors in the product does changes the product. You look at the conjugate, complex conjugate of the product. So what we said in lecture number 8 is this with V on the left side of each product, and this is how we should define the projection as well. It actually did not matter in number 1 and number 2 and number 3, and don't want to say it before I write it down, but I think it doesn't matter in number 5 as well, which is the most interesting part of the theorem. But here in number 4, in order to get 0 and not number minus or plus its conjugate, which is not 0, we need to write it down correctly. And continuing what we've already done in lecture number 8, we write down the vector v itself in the left coordinate of each product. Okay, that's how it should be done. Any questions about that? Okay. So, in order to prove number 5, which is interesting bit about the projection, the closest vector to V, but in our subspace, we need to prove an inequality. Which inequality we've already seen, we already know, we're familiar with. When it comes to norms, we have the triangle inequality, and we have Pythagoras. By Pythagoras, states that the norm of sum v1 plus v2 squared is always less or equals the norm of v1 squared and the norm of v2 squared. We want to use Pythagoras theorem here. Who's gonna be? Who's gonna call? Who's gonna be the exact vectors? So let's remember what we want to prove. We want to show that v minus u is greater than or equals v minus pi uv for every u in u. Let's use u. We need to show that difference between v and pi uv is smaller than the difference between v and u. Talking about the norms of the vectors. Now, we can write down the v minus u as v minus pi uv plus pi uv minus u. Now, on one hand, we've already shown that v minus pi uv is in the orthogonal space of u. This was number 4. On the other hand, pi uv is in u. This was number 1. And u is in u. So u is a subspace. Difference between two vectors in u is in u as well. So we have two, I mean, one should say it explicitly probably. It is good when the vectors are orthogonal, right? It's Pythagoras. That for orthogonal v1, v2, we have blah, blah, blah. So these two vectors, one is in U, one is in orthogonal space of U. They are both orthogonal. So this one and that one are orthogonal. And we can use Pythagoras. Can apply probably a better word. What does Pythagoras say? He said that the norm of the sum is greater or equal the norm of the difference, but I want to talk about v minus u. So it's v minus u, right? No, I want to talk about v minus, my bad. I want to talk about v minus pi uv, and not about v minus u. So let's change it. V minus pi uv is v minus u. No. Let's do it slowly. Slowly but surely. So we don't get any troubles. Okay, we have v minus w here. Pythagoras states that it is equal, not inequality, it's my problem. It's basic, some, I don't know, 7th grade geometry. We need to show that. Okay, that is totally fine. By Pythagoras, the norm of u minus v squared, v minus u squared are the same. What's the norm? It's non-negative. Is equal or less the norm of v minus pi uv squared, and is equal v minus pi uv squared and pi uv minus u squared. Is Pythagoras. It's equation, it's not an inequality. Probably very tired. And what do we have here? We have v minus u, the norm squared, is v minus pi uv squared plus something that is not negative. So if we take this not non-negative something and just delete it, we do get something smaller or equal. No. Yeah. So the norm of v minus u squared is greater or equal to the norm of v minus pi uv, and you apply square root. We do achieve that the norm of v minus u is greater than the norm of v minus pi uv. Pythagoras is not it is the way, but it's not an inequality. It's an equation, but when I give up of one of the components, it does become an inequality. So we proved number 5 as well. Full proof bar theorem. I want to write down another theorem, prove it as well. I think we'll make it till 2 and 30 minutes, and then have a corollary connected to the projection, corollary from this theorem, then we can finish. Any questions about our last proof? Number 5. Okay. Now, another theorem connected to the concept of orthogonal space, not necessarily to projections, but we will use it, as I said, to prove some corollary about projections. I call it the theorem, the orthogonal decomposition. Let's check out Wikipedia, if that's how you really call it in English. What the hell? No, can't find it here. Spectral decomposition or something else. I don't know. How do I call it in English? Orthogonal decomposition is fine. Let V be an inner product space over some field F And let U be a subspace of V, then the sum of U and the orthogonal space of U is V. Moreover, the intersection between U and U orthogonal is just the zero vector. In Hebrew, I call it Schum Yashar. Yashar, straight, probably not the right word for it. But you know what that means. Let's prove it real quick. We need to show two things. One, that U plus U perp is V, meaning that every vector in V can be written as a sum or as the sum of a vector from U and the vector from U perp. And secondly, that the intersection is actually only zero. You can write down the sum of the O plus. For one, let be some vector V. I want to show that V is the sum of some vector in U and some vector in the orthogonal space of U. But using our previous theorem, it's pretty easy. We can write that V is V minus plus its projection on U. Now, we show that by our last theorem, V minus pi UV is in the orthogonal space of U, which is section number 4 of the previous theorem. And the projection itself is in U, which was section number 1. So indeed, every V in V is the sum of vector from U and vector from the orthogonal space of U, which means that V is indeed, let's write it down explicitly. V is, or V can be written as the sum of the vector units. Means that it is U plus the orthogonal space of U. So this for the sum, we need to show that the intersection is 0 as well. But it should be pretty easy as well. Any questions about proof number 1? Let's march forward to proof number 2. We need to show that the vector inside the intersection must be 0. Let be sum of the U. Okay. One hand, V is in U. Okay. On the other hand, V is in U perp. So by definition, every vector in U is orthogonal to every vector in U perp. Specifically, it is true for V. I can think of V as vector in U, and on the other hand, in U perp. Now, by one of our basic properties of the inner product, when the product of vector with itself is zero, then the vector itself must be zero as well. By the non-negativity property of product, the positive definiteness, we conclude that V is zero as required. Yeah. So this is our theorem. And as I said, one last corollary about the projection we defined today, and we can finish before the material finishes us. Questions? Okay. So corollary. The projection of P on the space U. Why did you? Okay, on the space U is the same whatever basis of U you take, whether U1 to UK are. So nice formal language is independent. Let's write down more tachlis is the same whatever basis U1 to UK use, which by the way we defined it seems pretty intuitive, but formally there is something to write here down, and I use, of course, the theorem of the orthogonal decomposition. Proof that, I don't know, U1 to UK and V1 to VK be orthogonal bases for U. We want, let's call it, I don't know, B1. And this is B2. Long basis for U. By definition, the orthogonal projection. Not definition, but let's denote. We want to show that they are the same. We still don't know it. By the projection of V1 on U of V using the vectors of V1 and of course using the vectors of B2. Let's denote it with the projection of U with B2. And they are all V. Okay. As we already did in the proof of the orthogonal decomposition theorem, we know that we can write down V as V minus the projection of B1 plus the projection of B1, but on the other hand, as V minus the projection of B2 plus the projection of B2. Now, this one belongs to the streets, belongs to the orthogonal space, and this one is in U, as you already proved in the previous theorem, and used it in the proof of the orthogonal decomposition theorem, and it is true for the left side of the equation as well. This one is the orthogonal space of U, and this one is in U. Now, what do we have here? Two sums of an element of U and an element of U perp that are the same, that are equal. Now, U and U perp are not just a sum. It's what I call Nibros Chum Yashar. It's like at the end, we know that the intersection is zero. What is so important about such sums of vector spaces? When the intersection is zero, there is only, for every vector, only a unique way to write V down as a sum of U and U perp. So let's write it down and conclude our corollary. Now, V is U. We're ready to finish. U perp. So for every V in V, there is a unique way to write V as some as a sum, blah blah blah. So we do have that the vector here from U and the vector here from U are the same. It's one of the properties of these kind of sums where the intersection is zero. Okay, so to conclude our lecture today, the definition of the orthogonal, the projection is independent. Whatever you choose to be the basis, you get the same result. And as I mentioned, our next question 2 weeks from now, after a good reminder, is how do I find the projection when I don't have an orthogonal basis? One can ask it more generally. Having a subspace with some spanning set, how do we find an orthogonal basis? Okay, but we need to leave something to the next lectures. We're already finished. Sammy, any questions before I close the Zoom?
Not that I can think of.
Okay, so you got a question?
No.
No. Okay, so see you anything. You stay safe in the meanwhile.